ठीक है, अच्छा रात को वहीं पे खाना है। ठीक है, ठीक है। क्या करते हो? हाँ? आप पाँच का खाओ? हाँ? रे? पाँच बना लगा क्या?
हाँ वैसे
I think I'm not unmute.
Yeah, right, Danish, you're not on mute. So I'm audible?
yes.
Yeah, sure, good. Good evening, everyone. Today is the week 4, I think, in your course of Advanced Computer Network that you've taken as part of NPTEL. And as usual, I'll give you an introduction of what it is that you can expect today in the class, and how possibly you can leverage this class to do well in your exams and to solve the assignment questions. Right. So I believe almost all of you would have gone through the week 4 videos. If you have, it's great. If you have not also, it's fine. We shall look into it. Just one second. Just see if I can make people. Just give me a second. I'm trying to make sure that people get added without me sending them in. Okay, so I think now people should be able to join without me sending them in. Right? Okay. So I think mostly this week it was about traffic management. Right? So the bulk of the discussions were based on traffic management or revolved around traffic management. And so instead of teaching you the basics and then going on to the questions, I thought this time we could first look at the questions and then go into the topics as and when they are. All right. So I'll just give you a brief rundown of the questions that you can expect. I mean that we're going to discuss today, and we'll solve them one by one. Okay. I'll give you a few seconds to read this question. So, which of the following statements is or correct? Multiple of them could also be correct. So, differentiated services. So, I believe differentiated services is something that was taught this time. So, differentiated services, right? So, this was one of the main topics that was taken this week. And what was taught in the previous time, in the previous week, it was integrated service model, correct? This was week 3. 3/2. I don't remember exactly. Okay. So which of the following are correct or wrong? Let's take a look at it. Okay. Later or now. Next is again, which of the following statements are correct? We also learned this week when you would have learned something called the token bucket service model, and something similar to that is the leaky bucket model, which is used for traffic regulation. And you would have learned something called traffic shaping, and you would have also learned no, this is the previous one. So basically, these are the two main things that you would have looked at this week if you had watched the week 4 videos. The next question is based on token bucket algorithm, right? So we'll solve each and every one of these. But I thought I should give you context as to what it is that we're going to look at today. So we're going through all the questions first. So assume that we have a token bucket algorithm to regulate traffic. So if the tokens are arriving at a rate of 100 tokens per second, and each token has a size of 100 bytes, how many packets can be transmitted per second if the packets have a fixed size of 100 bytes? So I believe this is very similar to the question that you have in this week's assignment, right? You do have assignment questions this year. It's very similar to that. So we'll cover this when we talk about token bucket algorithm. And the next is leaky bucket. So it's the brother of token bucket. Bucket for traffic shaping. And imagine if this is the source of the data, and the data is transferred and generated and transferred in a particular rate. Okay, it's just nothing but the rate. Forget about this burst. What is the minimum buffer size required to prevent data loss? If the minimum sustainable transmission rate across network router is 5, then there should be maximum. Okay, let's see when we come across to it. This 5 Mbps. Right? So which of these would be so again, so we've gone through some keywords, right? So leaky bucket, token bucket. And question number 5 is, so you have multiple users. They're sharing particular channel which has a capacity of 10 Mbps. So if we use something called the max-min fair scheduling algorithm to allocate bandwidth to 4 people who want to share the same resource, in this case the resource is the bandwidth, how much would you allocate to each and every one of them? So we'll calculate how much would be allocated to each and every one of these people. And so this is once again max-min fair scheduling algorithm. And again, if the following statements are correct or wrong, which of the following statements are correct? Once again, differentiated services. So that's repeating all across questions. And you have something called the type of service. We'll see what that is. And then you have traffic shaping once again, and differentiated services. Right, so we'll answer this question when we come to it. Again, differentiated services. So I believe we'll concentrate on this differentiated services, and then we'll move forward. So in this case, what they're asking is what are the first 3 bits in the DS field indicate. So we'll look at the structure of the differentiated services fields and see what each of these bits correspond to, right? And now, once again, type of service. If you require, because someone requires normal reliability, so which bit of the type of service field should be set or unset? Again, this is the predecessor of DS. Predecessor would mean before DS came, there was type of service, right? So which of these is the correct answer? And packet P needs to be sent with assured forwarding class 4 with medium drop preference. So once again, this is part of DSCP discussion, differentiated services code point. So what is a binary sequence corresponding to this class to be set in the DSCP field of packet P? So every packet has a header, and we need to see which of the bit sequence has to be set to achieve this assured forwarding class 4. And what is the number of bits that are reserved in the type of service field? So what is the number of bits that are reserved? These are all very simple questions. So I believe the heavyweight questions are question number 3, 4, and 5. Okay. So once again, differentiated services, token service bucket, leaky bucket, traffic shaping, again token bucket, again leaky bucket, max-min fair scheduling, and differentiated services, type of service, differentiated service, type of service, and assured forwarding class, which is once again a part of differentiated services and type of service, right? Okay. So in this context, let's move ahead with the session today. Okay. So the main topic that was spoken about is traffic management. Okay, so the context here is, I once again go back to the same diagram that I've been drawing for the past 3 weeks. Might be bored by this point, but bear with me. So this is you, and you are a part of a network. And this network has multiple laptops, or rather multiple nodes. And every such network has a border router. Spoke about this in the very first class also. All the traffic from these nodes go through one of the border routers, and then it goes to something called as the internet, which is pretty much nothing but a network of networks, right? And the entry to any such network happens through something called as the border router. And this is the destination network where you have the server. So this is the server. And this also has a border. So essentially, I think by this point, you must be aware of this, that be it your campus or your office or anything, there is a boundary, and there is finally one machine or one router through which all the traffic from your boundary, or rather from your organization, passes through, and that is called the border router, edge router. Okay, so typically what happens is, this network is under one administrative boundary. So this network is under one administrative boundary, in the sense, whoever is governing this network has certain amount of control over how the nodes or how the routers inside this network behave. This is not the only router here. This is the edge router. You have multiple routers inside also. We cannot discuss that in the diagram. And so this is pretty much how networks work in the current state of the art. By that I mean today. In today's world, this is how routers work, or rather how network works. But now we are concerned with the traffic management aspect of it. So if you ask, what is this traffic management? Now it is very, very simple. So what is this traffic management? We can say it in layman's terms also. You manage traffic. You manage traffic. Okay. So what is this traffic? Traffic is nothing but set of flows. And what are flows? Set of packets. And what are these packets? Set of bytes. And what are these bytes? Set of zeros and ones. So that's pretty much what it is. So whatever it is that I want to put on the wire, for example, let's say they want to put on the wire, of course, it does go in the form of packets. So we show them as packets, but in the end, they are all nothing but bytes, which are nothing but sets of bits, which are zeros and ones. Okay. So in a network setting, at the border router, we see a lot of flows, traffic. So there are scenarios and cases in which some of these flows are more important than the other flows. Some of them are more important. Are more important. What do I mean by important? Let us say you are streaming a sports game, IPL or whatever it is, right? So you're getting traffic to your laptop, right? You're getting traffic. So even if one of these packets are missed or one of these packets are gone, since you're watching it live, you're not going to go back and look at what's happening. So you'll just have a bad pixel on the screen and then you move on, right? So in a relative term, these set of packets which are used for live streaming are less important than packets which carry your bank data. Most probably it is a TCP stream and this is a UDP stream. I believe you know what is TCP and what is UDP at this point of time. Uh, so in a way, in case of any congestion or in case of any scenarios where you have to prioritize one packet over the other, the router will definitely prioritize this instead of this. Right. But this is not the only case. There are multiple cases and multiple ways in which you want network to behave. For example, some of these systems are having more priority. And that means this router has to prioritize the traffic that comes out of this system more than these systems. So in a way, every organization, every network has their own way of have their own requirements in terms of prioritizing certain types of traffic. And that is what is accomplished by traffic management. Right? And it might also be the case that um, so this traffic management, right? Sorry, this traffic management could also happen in mostly it tends to happen at closed networks, private networks, but some of these algorithms are also open for the internet or rather the core network. So the motivation for this is how to discriminate better. Right. So it's okay to discriminate between packets. That's completely fine. It's not okay to do it in real life. Okay. So how do we discriminate better? So what are we going to discriminate based off of? We are going to discriminate based off of the traffic. And what is traffic? It is a set of flows. What is flows? It's a set of packets. Right. And what do these packets have? They have header fields. So every packet that goes on the wire has a header field. Okay. So let's look at a very famous header field. header field, which is IPv4 header field. Okay. So I'm repeating all these things just in case some of you do not are not coming from a networks background where you've not probably taken a computer networks course, or if you've taken it and you've not understood things properly, then there's a chance for you to rehash all of those. For people who are familiar with it, bear with me. Once I go to the sums or the questions, it might be beneficial to you to understand how to solve these questions, right? And as usual, this is always recorded. You can also go and take a look at the uh, recorded video on YouTube. I'll be posting it either today or tomorrow. And if you have any questions, no matter how basic it might seem to you, now is the time for you to ask. It's completely fine. This can also be a completely discussion-based session where I can also learn from you and you can learn from me. Right? It's an opportunity for you to open up and interact. Okay. Right. So IPv4 header field. Usually I tend to ask questions to people in the chat, but maybe that'll be like I'm pushing you to respond. So it's okay. You can be at your comfortable state, and I go ahead and feel free to unmute and speak whenever you want. Okay. So let's go into the IPv4 header. Okay. So what is this header field? It's nothing but a set of bits on every packet. But what is the speciality of these bits? They are structured according to a predefined way. And what is this predefined way? It means that no matter which computer or where I am in the world, if I want to send an IPv4 packet, I need to follow a particular structure. And this structure is described in something called RFC. So there are multiple RFCs, which is nothing but request for comments. This is nothing like a publication or a set of rules that are published. Okay? And any networks or any person who wants to communicate or build algorithms have to comply to these RFCs. Now, what if I say I don't want to comply and I do my own type of header? It simply won't work, because networks is something that works because everybody agrees to a particular predefined notion, right? So if I'm sending a header field like this with 3 fields, and I'm sending it here, but the RFC says it only has to have 2 fields, then this person who's receiving 3 fields will not know, because all that he's following is the RFC, but I am not following the RFC, right? So he does not know what is this third field. He'll be like, what is it? The data is corrupted. So in essence, so every node or every system that is having a network stack has to follow the RFC. And what is this RFC? What is it saying about IPv4? It is giving us a particular structure. Let us look at that structure. Let's look at it. Maybe I should have put a picture of this, but it's okay. I'll do that next time. Okay. So this is basically the format of an IPv4 header. Now you might ask, why did they make it like this? They made it like this because of certain reasons that they felt would be required at that point of time. So this was all built, I think, in 1990s or 2007, 1990s is where the header fields, RFCs, they were all finalized. When the internet started coming up, network started coming up, that's when they finalized all of this and they made it in a particular way. And fortunately or unfortunately, we are still using similar structures without huge differences. And this is actually what is causing the problem of security and all of these aspects, because we cannot fundamentally change the way the internet works, because almost every node, every router, everything is hard coded to follow this particular header structure. If suddenly tomorrow they give a new RFC saying change it, put version number here, put version number here instead of somewhere else, then the internet will break. So that's why any change in the internet takes a lot of time, or any change in networks. If tomorrow I find a new way to represent header fields, which is more efficient or which solves most of the problems by adding some extra fields, let's say, it may not be immediately adapted, because starting from the hardware implementation of network protocols, which is of course IPv4 is also part of it, it needs to be changed. So networks evolve very, very slowly. Coming back, this is what it is. So what I've written here is this is the bit number 0, bit number 4, 8, 16, 31. So total, how many bits are there? There are 32 bits, including 0. So what is 32 bits? 4 bytes. So this one row is 4 bytes in length. Okay, so this is 4 bytes in length, and you can see there's something called version, something called header length, something called total length, identifier, time to live. We discussed this previously in one of the classes where we spoke about trace route, and then the protocol, header checksum, source IP address. You should know what source IP address is, destination IP addresses, and options. If at all you've enabled options, you need options, and then whatever data that you want to encapsulate. Right? This is the application data or whatever it is that comes from the top, from the above layers. Okay. So, but what we are going to talk about today is one small tiny part inside this field called type of service. It's called the TOS. Now, this is also called as differentiated services. Okay. So why is it called by two names? So when they came up with this TOS at some point of time, maybe 1990s, at some point, let's say 1992. It's not the right date. I'll just give you an example. They named it as type of service. And in a later time, when things evolved, 1996, let's say, they call it differentiated services. So basically, they changed the way these bits are to be interpreted, right, through an RFC called request for comments. Okay, so in this nomenclature, in this uh, context, let's look at what type of services, because we have some questions on type of service we just saw. And let us also look at what differentiated services is and how it evolved from type of service. Okay? I'll be brief about this because this is also described in the videos that you would have seen. Okay, so this type of service. Okay. How many bits are there in type of service? So it starts from bit number 8, or rather 9. So basically there are 8 bits, right? So this basically contains 1, 2, 3, 4, 7, 8 bits. Okay, so 8 bits. All right. Five, 6, 7, 8. So these are 8 bits. Okay. So the fundamental idea here is based on the combination of bits in the type of service field. This is the type of service field. Okay. The router will behave differently with the packet. Okay. Now let me elaborate on that. So if there is a router, a packet comes, the router takes the packet, checks its header field. This IPv4 header field is also there. That IPv4 header field, there is something called type of service. Okay. If the router finds, for example, I'm giving an example, the type of service field has all ones. Just an example. Then the router is told that, okay, this is a very important packet. You need to send it out as soon as possible. So even if there are multiple other packets waiting to go out, it will put this packet at the top of the list and will send it. And if it had 00000, let's say, instead of 111, it had 0000, then it would not do anything. It would just put it in the normal place in the queue. So essentially the idea is I fill something up here, I fill some combination up here like this, and based on that, my router will behave in a different way with the packet. With the packet. So so how or what are the combinations? Let's say now in this scenario, the first 3 bits. These are the first 3 bits agreed. Bit 0, bit 1, bit 2, bit 3, bit 4, 5, bit 6, bit 7. The first 3 bits is called IP precedence. and the next 3 bits, let's not look at it as the next 3 bits. So okay, the next 3 bits are, you can say, they are also decision makers, or I don't know what name to give it. So what's going to matter essentially is these first 6 bits. That's all. These 2 bits they're not using. Doesn't matter what is there. The router is going to skip it. They'll only check what is there here, 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 and here, and take a decision appropriately. Okay. And what do these last 3 bits mean? They basically denote the delay, and then the throughput, and then the reliability. Okay. So we'll come to what this means. So delay, throughput, and reliability. So now we know, what do we know about type of service? Only 6 bits are used by the POS field. What about the 7th and 8th bit? It was kept reserved for future use. If in case in the future you come up with a new protocol, a new way to do things better, then you can use the 6th and 7th bit. This is what they said. Okay. So now the first 3 bits, correct? IP precedence. So with 3 bits, which is basically 1, 2, 3. So with 3 bits, right? What are all the combinations? 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This is basic decimal computation, right? So with these 3, by the way, giving a context, we're talking about the first 3 bits, which is called IP precedence. And what is the decimal value of this? This is 0, 1, 2, 3, 4, 5, 6, 7. Okay. So this means something. What does it mean, and who defined it? It is the people who wrote the RFC. What do they define? They define that if it is 0, 0, 0, treat it as routine or normal. Don't give it any thought. This person is normal. This packet is very normal. If it is 001, it's called priority. Now you can say priority is greater than normal, but it is still down there. Okay? And if it's more, then it's immediate. Immediate means like just send it right now. And if it is more than that, these are just nomenclatures or terms that they've used. Flash, and then something called flash override, and then you have critical, and then inter-network control, and then you have network control. So essentially, these are all just fancy names that are given to certain packets to make them treat normal. Now, an example would be if you're a VIP, then probably you'll have this label on you, which means if you let's say if you go to a cricket match, let's say, then this is equivalent of sitting in a box. a box would mean, of course, you get food served to you and all of that, right? And 000 is the people who sit outside in the stands, who definitely have a better time, but yeah, but they don't get anything special. So this label, so every packet is given a label, and the label is given through IP precedence. It's as simple as that. If I want to send a packet and I want to make sure that my packet is treated well, rather it's given the highest importance wherever it goes, then I will just set 111 in its TOS field. It's basically going to be here 1, 1, and 1, and it will be treated accordingly by all the routers that it encounters. But the router also has to be configured to follow DSCP. In a sense, it needs to be enabled in that particular network. Okay. Now the first 3 bits are spoken about. The next 3 are delay, throughput. They're running late, so I think I'll go a little bit faster. Delay, throughput, and reliability. The next 3 bits. Delay, throughput, and reliability. And reliability. Okay. Now once again, here also you have the same combinations, right? 0, 0, 0, 0, 0, 0, 0, 1, yada yada, 1, 1, 1. So basically, what this says is, if delay, correct? If the delay bit is 0, then it's normal. If it is 1, then it's low delay, which means the delay in that for that packet should be as less as possible, which means it's a higher priority for it. Okay, and the next thing is throughput. Throughput. So the throughput bit is 0. This is 0. Then is normal. 0 means normal, and 1 means high throughput. What is throughput? It's the it's a metric that talks about the total number of packets that are forwarded. Let's say in this case, and reliability. So reliability is also a very vague term, but you can think of it as, okay, I won't drop this packet. Reliability is set to 0, then I might drop it if it is pretty much normal, and if it's set to 1, I might not drop it. So essentially, with a combination of these 6 bits, you could differentiate between different types of traffic. So what are we doing here? We are differentiating and discriminating between different types of traffic. This is the punchline. The punchline is we are differentiating between different types of traffic. Okay, now what was the problem here, or what went on? What went on is networks evolved, and more requirements came up in terms of you can say networks evolved, the way data centers worked, they evolved. So more use cases came up, and they changed this. They changed this TOS, this version 1 of TOS to version 2. What's the difference in version 2 of TOS? Same 8 bits only. Correct. 2, 3, Same 8 bits on. Nobody is changing the fundamental structure of the IPv4 header. But the way these 8 fields are considered, first 3 bits, same IP precedence. Next, previously it was next 3 bits. Now they've used one more bit here. Now they're saying it's the next 4 bits. Now I'm using this, and this. Previously only these 3 was used. But now I'm going to use this one and I want to leave this for future. See, similarly, how these people, when they came up with these, they left this and this for future. So in the future, which is basically version 2, they've used one more bit here. So that's basically the idea here. Okay. Now with one more bit that they've used, it is also very, very similar. The meanings are all very, very similar. In the sense that IP precedence remains the same, 000, 1, 1, 0, yada, yada, yada. And similar to that, if all of these are 0, right, these 4 bits, then this is normal service. Normal. But if I'm going to say 1000, then it means minimize delay. Minimize. Similarly, there are 3 more configurations, correct? A total of 5 configurations, including 0. That mean that basically say treat this packet in a particular way: minimize throughput, maximize reliability. Okay, so this was version 2 of type of service. Till now, we are only looking at type of service, version 1 and version 2. So then came certain use cases. All of this is detailed in the class lecture. Is right in it. Then came something called service level agreements. So essentially what this means is, let's say there is a cloud provider. Let me not say cloud provider. Let us say there is one organization, or let's say a company. Right? Now this company is storing a lot of videos. Right? People request for videos and it sends videos back. Simple. Now this company will have certain SLAs, service level agreements, with its provider or with its equipment manufacturer. And what this means is, I want, one of these things could be something like, I want there to be no delays greater than 100 milliseconds. Now this is one service level agreement that the company has with some of its providers. Now, how do you meet such kind of agreements? You need something called either type of service or its advanced version called TS. Okay. So this was the first implementation of type of service, which was actually adopted and used all across the internet. If in a nutshell, if I have to say what this is, it is nothing but a framework and a building block to enable deployment of scalable service discrimination in the internet. Service discrimination, and that's where the word service also comes from. Okay? Okay, so what this does, right? This is you. You're also part of the network only, and there's one more router here. Okay. Now there may be multiple routers here. There may be multiple routers here. There may be multiple routers here also. So as soon as your packets hit this router, you set some bits. And then you send the packet across. As soon as it exits this boundary, it might remove those bits. And once again, as soon as it enters here, it sets some bits. And as soon as it exits here, it might unset those bits. So essentially what this is saying is all of these things are making some changes to the packet. What changes in the DSCP field? And they're nothing but bit changes. So essentially, this is nothing but packet marking. So this is what is called as packet marking. It's a packet, and I'm marking something in that packet to make it look special or to make it look different. I'm marking it. Called packet marking. So where all is it done? It's done at the edge router or at the first hop router or administrative boundaries. Okay. Now this administrative boundary is once again a subjective term, but we spoke about this in the beginning of today's class, that it is a set of nodes or set of routers that are under the control of one particular administrator. Okay, that's an administrative boundary. So coming back to this, if you set some bits here, these routers in between, right, they will treat the packet in a particular way. And if you set some bits here, you will set some packets in this. I mean, sorry, if you set some bits here, these routers will treat the packet in a particular way. Similarly, if you set some bits here, these routers will treat the packet in a particular way. And that's what the DSCP does. Now, what are all the fields in a DSCP? Okay, so how many bits are there in DSCP? 8. Why is it 8? It is nothing but the TOS field. We saw here, right? It is nothing but the same TOS field with 8 bits. We have just rebranded those 8 bits and we have renamed it. That is what DSCP is. It's nothing. So we've understood TOS. The DSCP is also very, very similar. It has got the same 8 bits. Okay. Now, what are all those 8 bits? Let's take a look. So what are all those 8 bits? Bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, 6, and bit 7. Okay. Zero, 1, 2, 3, 4, 5, 6, and 7. Yeah. Okay. Similar to the TOS field, So similar to the TOS field, the first 3 bits, okay, this is called as the class selector, and this is called drop precedence. So that is all that it is. This is called the class selector, and that is called as the drop precedence. This does look very similar to the TOS version 1 that we saw. It also used 6 bits only, and these 2 bits ignore for now. This is basically for ECN, explicit congestion notification. Let's not worry about that for now. So the whole game happens with these 6 bits. Okay. If you had seen the class video, you might have noticed a table that was given there. I think drawing that table would be too difficult, so I'll abstract certain things from it. Essentially, there are 2 classes. Okay, 2 main classes. Assured forwarding. Okay. 2 main classes. Assured forwarding and expedited forwarding. Okay. So this assured forwarding has 4 classes. I mean, has 4 types. So one is priority, priority. The second one is immediate. Third one is flash. And the fourth one is flash override. Okay. So the combination of these 3 bits, right? So we have 3 bits that we have to set to enable this priority is 0, 0, 1. And the combination for this is 0, 1, 0. And the combination for this is 0, 1, 1. And the combination for this is 1, 0, 0. Okay. Now, if it is 0, 0, 0, this is nothing but the default or normal. Default or normal. This is basically equivalent to the common man. And the more higher you go, the more upper you go, the more bigger of a VIP you become. Correct? So this is a higher class. And beyond this, there is something called expedited forwarding, right? So expedited forwarding has a combination of 1, 0, 1. So what are all the combinations that we have covered here? We have covered 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0, and 1, 0, 1 also. What are the 2 things that are left out? 1, 1, 0, 1, 1, 1. So these are also having some meaning, but let's forget about that now. So these are the 4 classes, right? 4, sorry, not these 4, right? Priority, immediate, and then this one is expedited forwarding, and these are all called assured forwarding. So these are the 5 classes, 5 main classes. And okay, now beyond these 5. Right? Beyond these 3 bits, you have another 3 bits, right? These 3 bits could also have multiple combinations. Okay. So each of these classes, right, also have 3 bifurcations. And this is basically the drop precedence, which is low drop precedence, medium drop precedence, high drop precedence. Is a drop precedence, right? So let us take, let's say, 0, 1, 0. And if I am writing 0, 1, 0 here, then the drop precedence is going to be low. Okay. If I am writing 0, 1, 0, 0, then the drop precedence is going to be medium. And if I'm writing 1, 1, 0, it's going to be high. So it's basically like you're bringing these 2 bits together. Okay? These 3 bits, and these 3 bits. If you bring them together, they form some meaning. So all these 6 bits have a particular set of meaning. And what does this drop precedence mean? It means if in case there is congestion, or if in case the router is not able to process the packets, it needs to be able to choose some packets to drop. Which are all the packets that it will be dropping depends upon whether it is low, medium, or high. If the precedence is low, then that will be the first packet that is chosen to drop. If it is high, then it might not drop it unless and until there is no other option, no other choice. Okay, so this is what a differentiated services field is. There is nothing more to it. Okay. Now, this differentiated services, they govern the per hop behavior and all these aspects. You can take a look at the video that is there for that is there in the NPTEL site. Okay. But now let us start looking at. Now we are at a place where we can look at the questions. Okay. Now let's look at the first question. We already went through the questions in the first 10 minutes. So, which of the following statements is or correct? Okay. Differentiated services, we just saw what differentiated services is. It provides guaranteed quality of service. See, it definitely tries to provide a good quality of service, but it cannot guarantee it. It tries its level best. If I'm going to put a priority of 111 everywhere, let's say in the differentiated services field, and make my packet the VIP, even for a VIP, if uh, if on that particular day the road is broken, then nothing can be done. Right? There are limitations there also. So you cannot guarantee anything. So this is once again best effort. Best effort, but a little more than best effort in the sense I'm doing as much as possible, but even then I cannot guarantee it. So this is wrong. The second is differentiated services allocates resources on a per class basis. Yes. So we looked at these things, right? Something called class selector. So based on a class, I am going to allocate resources. Allocate resources would mean the router is going to allocate as much resources as this particular class of packet deserves. That's it. So this is correct. And differentiated services reserve resources on a per flow basis. If you remember from last class, per flow basis is very intensive on all the routers. So along the path, if you have to reserve, like basically say that 10% of CPU of the router is allocated for flow 1. So this means that nobody else can use the 10%. It is very, very costly to the router. And who does this? It's not differentiated services, it's integrated service model. I don't know if you remember this, but so integrated services model reserves resources on a per flow basis. So this answer is, sorry, this statement is wrong. And next is differentiated.
Hello. Harish, your voice is not audible.
Your voice not clear, sir.
Now I should be audible.
Yes, you are. You are.
Right, thanks. Okay. Right, we were answering questions related to DAC or differentiated services. So just rush through some of the easy questions and I'll go to the numericals as fast as possible. Okay. So, by the way, what are the first three bits in differentiated services field indicate? This is pretty much a no-brainer, right? We just looked at it. So what does it indicate? It is nothing but the class selector. Nothing but the class selector. And I think two more questions are also similar to this. Question number 8 and 9 and 10. 8 and 9. All of these are about TSCP or TOS. Okay, question number 7 is done. Now let's go to question number 8. 9 and then 10. Okay, so question number 8 is now, okay, so if a customer requires normal reliability, the keyword here is normal reliability, which bit of the type of service field should be set or unset? Is it the fourth bit, is it the fifth bit, is it the third bit, or is it the third bit? Okay, in the sense, what should these bits be set to? So if they're talking about the type of service. Okay, and what does the customer want? He wants reliability. Now, when they're talking about this type of service, it's type of service version 1. Okay, what was version 1? Version 1 was over here. So what it did, uh, what is the structure? Bit, 0th bit, first bit, second bit, third bit, fourth bit, fifth bit. Okay, we're going to play only with these 6 bits. Okay, but they are taken from 0. So they want normal reliability. So there is delay, there is throughput, and there is reliability. So reliability is basically the bit number 5. So if bit number 5 is 0, then it means normal. If it is 1, then it means high reliability. Okay. So what does the customer want? The customer requires normal reliability. The customer requires normal reliability. Normal is nothing but 0. So with which bit is it? It's the fifth. Sorry, it is the bit number 5. Number 5. Okay. So this is again directly following the definitions of how these things have been set up. And again, a packet P needs to be sent with assured forwarding class. So what is assured forwarding? It is AF, right? We were looking at DSCP and there was 2 major bifurcations: assured forwarding and explicit forwarding. Expedited forwarding, sorry. AF and EF, correct. So in the assured forwarding class, in the assured forwarding, he wants to use class number 4. So in the assured forwarding, zip 1, 2, 3, 4. Right. In assured forwarding, I said class number 4. So there is class 1, class 2, class 3, class 4. What is class number 4? Class number 4 is flash override. Okay. So far, just from the question statement, I know it is assured forwarding. It is class number 4 and with medium drop preference. With a medium drop preference. So there were 3 preferences, right? It's either low, medium, or high. Correct? They want to use the medium drop. So what are the combinations? Assured forwarding plus class 4 plus medium. So for assured forwarding, there is class 1, class 2, class 3, class 4. Right? So the class number 4 is flash override. What is the combination? It's 100. Okay. So I'm just writing down 100 over here. I know the first 3 bits is going to be 100. Clear enough? Now what will be the next 3 bits is the question. For this, if you want it to be medium, it is going to be 100. This 100. Right? So if you combine this and this, you're going to get the answer to that question. So it's 100, 100. And of course, this for to answer this question, you have this huge table that was shown in the class videos. So just follow that and you'll get the answer. But if you want to remember it, then there's an easy way to remember it. In this case, you only have to remember these 4 combinations and these 3 combinations. And if you mix and match, you're going to get class number whatever it is. Class number 2 plus I, then 0, 1, 0 plus 1. Okay. Now that's it. And then finally, how many number of bits are reserved in the type of service field? Okay. But when I was talking about type of service, once again, when they say type of service, right? This type of service version 1. Okay. Look at version 1 only. So the type of service field. So yeah. First 3 are taken. Next 3 are also taken. So these are all reserved for future use. Correct? So answer is 2. 2 bits are reserved for future use. And they generally just call it as reserved. Okay? So with this, we've finished DSCP and TOS. Now let us dive directly into the questions. We don't have time to talk about the basics of leaky bucket and token bucket, but probably while answering these questions, you'll understand. Okay? So we have 4 more questions to go through. 3 of them are numericals. Okay, so which of the following statements are correct? So there is something called token bucket model. There's something called leaky bucket model. Now, where are these used? Where are these algorithms used? Token bucket, leaky bucket. It's traffic policing and shaping. Now, if you had watched the videos, you'd understand that traffic policing and traffic shaping are pretty much the way in which you affect the traffic. And where does this happen? This happens at the router. Okay. And token bucket is used for IP-based networks. and leaky bucket is used for ATM networks. Now you would have heard of what IP-based networks are because that's what we're using right now. Now these ATM networks are a type of network in which the packets, right, they're all of the same size. But in IP networks, the packets are variable size. Some of them may be 1500 bytes, some of them may be 4000 bytes. We don't know, right? The data, it all depends. So in the ATM mode, this is not the case because that's how they designed it. Once again, in networks, anything that we talk about it with the perspective of how the designers intended it to be, how the designers designed it. ATM was designed like that, and that's how it is going to be. The buck stops there. Okay. So essentially, the objective of leaky bucket and token bucket is to basically regulate the rate at which traffic flows. Okay. So how do they do that? We'll see when we look at the sums. Okay. So once again, this is correct because token bucket model, it is used for IP-based networks. Leaky bucket is used for ATM networks. So what are the difference? Packet size. That's it. So this is second answer. Second is also correct. And traffic shaping regulates the speed of traffic that is leaving an interface. Yes. And what do you use for traffic shaping? You use both of these for traffic shaping. Okay, you use these algorithms for traffic shaping. And what does it do? It regulates the speed of traffic, the rate of traffic, or rate, whatever you want to call it. Okay, so this is also correct. And per flow based resource reservation puts pressure on the network routers. So once again, per flow based resource reservation, where does it happen? It happens in integrated services model. Correct. And that reserves resources based on the what do you call per flow. Flow is nothing but a set of hierarchies. I explained what a flow is in the previous session. If you want to take a look at that class. So if there are 10 flows, then for 10 flows, you'll be dividing a router into 10 pieces. And if one of those pieces don't work, one of those flows are not happening, then it's a waste of space, at least for until that part of the router is reassigned to some other flow. So it is not a very efficient way of doing things. And it's for practical scenarios, it is not going to work out on a daily basis. Okay? So definitely it does put pressure on the network routers. Now, we spoke about token bucket and leaky bucket. Correct. Let's look at a question on token. So assume that we have a token bucket algorithm to regulate traffic. Okay, we are using token bucket algorithm, and token bucket is used for which kind of networks? It is for IP networks. Now, if the tokens are arriving at a rate of 100 tokens per second, okay, tokens arriving at 100 per second. Okay, at first second, you'll have 100. Second, you'll have 200 tokens. Okay, you'll have 200 tokens. And similarly, at the third, fourth, fifth second, you'll have 300 tokens, 400 tokens. Now, what I would do is I'll have a bucket. Let me say I have a bucket or a thali or whatever. and I'm accumulating all of these tokens. First I'm saying 100 token, then I'm saying 200. The first 100 over here. Sorry, first I have 100 tokens, then 100 became 200, and then it became 300. There's 400 tokens, 500 tokens. Right. So I can accumulate more, just like Lord of the Rings. I can accumulate as many tokens as possible. Tokens are good. Tokens are great. Keep it like that. The more tokens I have, the more power I have. Okay. Now coming back to this, there are 100 tokens per second. Each token has a size of 100 bytes. Okay. So how many packets can be transmitted per second if the packets have a fixed size of 100 bytes? Okay. Fixed size of, sorry, 1000 bytes. Right. So basically the token bucket algorithm is used to regulate the rate of traffic in a network. So how it works is it allows the transmission of packets. So basically what happens is there are packets coming like this. So this is a link, let's see. This is the link, this is the sender, this is the receiver. Okay, sender, receiver. Now you have packets that are coming like this. And this is the router. Now the router has to regulate traffic. If there are 10 coming here at a particular instant, then maybe it will send it back like this at this rate. Possible. So how does it do it? It does it based on the tokens that it has accumulated. Okay. So it is given that tokens are arriving at 100 per second. Okay. And what have they given here? They've given that each token has a size of 100 bytes. So what that means is if I have one token in my hand, then I can send 100 bytes. Okay, let's keep it simple. If I have one token in my hand, I can send 100 bytes. One token equal to 100 bytes. The value, right? Bytes. And this is which means I spend one token and I can send 100 bytes here. If I have 100 tokens here and I take one from it, so this becomes 99, and I exchange that one token for 100 bytes and I put the 100 bytes over here. Okay, so this is essentially how this token bucket works. You exchange tokens for bytes, and they've given the value of these tokens also. One token is equal to 100 bytes. And what is the capacity of this bucket? The capacity of this bucket is 100 tokens, correct, per second. So what I failed to tell you at the beginning is the capacity of the bucket is always defined with respect to the per second arrival of tokens. So when I said 100, 200, 300, that was just an example. Maybe you're wrong. Maybe it was not the right example to give it. So when I say 100 tokens per second, then that means the bucket can hold a maximum of 100 into 100 bytes, because one token is equal to 100 bytes. So 100 tokens is equal to 10,000 bytes. So 100 tokens is equal to 10,000 bytes. So essentially, it can transmit 10,000 bytes of data per second. That's essentially. So all this going around and coming has translated to 10,000 bytes. This is the capacity of this bucket. Okay, now we've understood what the bucket is, what is the capacity of this bucket, and the question here is how many packets can be transmitted per second if the packets have a fixed size of 1,000 bytes. So they have said that all of these packets are of 1,000 bytes. This is 1,000 bytes. This is 1,000 bytes. 1,000 bytes. This is 1,000 bytes. Okay. So right, that's pretty much what they've said. So let's take this packet. For one packet is nothing but 1,000 bytes. How many tokens are required? Tokens are required. One token equal to how much? 100 bytes. So to divide 1,000 by 100, the number of tokens per packet equal to 1,000 by 100 is equivalent to 10 tokens. Okay, so we know that to transmit one packet, it is going to take 10 tokens. So therefore, the maximum number of packets that can be transmitted per second is how much? So we know 10 tokens is required per packet. Okay, I will written this. So how many tokens do we have? We have 100 tokens per second. So out of 100, if I divide this by 10, there's nothing but number of tokens per packet. So now we will know how many packets can be transmitted, which is 10 packets. Right. So essentially, instead of giving you all this explanation, could have also easily said we have a capacity of 100 tokens per second. Right. So how many tokens are required per packet? 10 tokens are required. So therefore, how many packets can be sent? 10 packets. That's it. So the answer here is B, 10. Now, this is basically the long short explanation that I've given you. You can also procedurally do this very simply, okay, by just following through the logical steps that I've given. Right. So now that is about token bucket. Now let's look at leaky bucket algorithm. Token bucket, leaky bucket, all of these are all the same thing, but for different networks. So in leaky bucket, oh, I think I said something. Oh yeah, I'm right. So now we have a leaky bucket. Now here it is for ATM networks, which means the size of packets are all the same. Okay. So consider a network that employs a leaky bucket algorithm for traffic shaping. Traffic shaping is what these algorithms are required to do or are made to do. A system injects 25 megabytes of data into the network. 25 bytes. Okay, be careful. Megabytes, not bits. So my experience, whenever you get bytes, change it into bits. So how much is 25 megabytes equivalent to in bits? So it is 25 into 8 mega. Multiply that by 8. How much is this? It's 200 mega. That's it. So I want to transmit 200 megabits into the network. This is my objective. The big O. I want to transmit this much of data into the network. I don't care which network, whatever it is. I want to just transmit this. Now this says that the data is generated and transferred in a burst of 10 Mbps. Okay. The rate of data generation is also given, and that is how much? 10 Mbps. All right. So what is the minimum buffer size that is required to prevent data loss if the minimum sustainable transmission rate across the network router is 5 Mbps? Okay, so I would like to simplify the sentence that's given here. What is the minimum buffer size required to prevent data loss if the minimum sustainable transmission rate across network router is 5 Mbps? Now, I think the question is slightly off base. It must be maximum if I'm not wrong. But either way, in this question, in such kind of questions, you will the limit the value that's given here is basically the limit, which means you cannot go above that. It literally cannot go above that. Okay. So the limit, call it the limit, is equal to 5 Mbps. Now, one happy news is we have this in megabits, bits. Okay. We have this also in megabits. We have this also in megabits. These are the 3 data points. Now we have to play with these 3 data points and try and solve this question. Okay. But before that, I want to draw parallels. Now, what this leaky bucket does is, imagine there is a bucket, and this bucket is nothing but a router. Packets are coming, and packets have to go out. So what I'm doing is I'm going to collect all of these packets into the bucket. Okay, I'm going to collect all these packets into the bucket, but the hole I'm going to put is going to be smaller, which means if I'm collecting 10 packets, not all the 10 packets can flow through. Maybe 2 or 3 can flow through at 1 second instead of 10. Essentially, this is what it is. So this buffer, what they mean by buffer is this one. And this happens at all the hops, at all the routers. So what is the minimum buffer size that is required to prevent data loss if the transmission rate is 5 Mbps? So when they say 5 Mbps, yeah, when they say 5 Mbps, see this hole over here. This is 5 MB, which means it can sustain 5 Mbps of traffic. In the sense, you can only send 5 Mbps of traffic. And unfortunately, what is the input of traffic? It is 10 Mbps, which means this bucket will keep getting full because the output is lesser than the input. And that's pretty much what we are trying to do with leaky buckets. Correct. You are regulating traffic. You are reducing the rate of traffic. Okay. And how much of data am I putting into this? I'm putting 200 megabits. And this was 25 megabytes. Now that I've converted that into this percent. So with this idea, right? Let us solve it. Now they have given that I'm going to send 200 megabits, correct? So, but for how long? Listen, I need to find out the duration. Burst duration. Now the burst duration is equivalent to whatever I'm trying to send, which is 200 megabits divided by what the rate at which I can send it, which is 10 Mbps, 10 megabits per second. So cancel, 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 and you get 20 seconds. Fair enough. So what essentially this 20 seconds means is when they said 25 megabytes of data into the network is going to be done at 10 Mbps, how long will it take to transfer this 25 megabytes? It is going to take 20 seconds. That's all. We want to know the duration of the transmission duration or whatever it is, the time it takes to send all of these 25 megabytes or 200 megabits into the network. It's going to take 20 seconds. Now, we know the time. So in 20 seconds, how much will the router transmit in 20 seconds? How much will the router transmit? How much can the router transmit? It can transmit only at the rate at which this hole is defined. And how much is it defined as? This is defined as 5 Mbps. This given here is 5 Mbps, right? So how much will the router transmit? It will transmit at the rate of 5 Mbps. But for how long? For 20 seconds. So therefore, total is 20 into 5, which is equivalent to 100. I'll type the units also. 20 seconds into 5 megabits per second equivalent to second cancel. So you're going to get 100 megabits. So this is what the router can transmit. Correct. So 200 megabits are coming in. And how much is going out? Coming in. How much is going out? 100 megabits are going out of the bucket. How much is left out in the bucket? Left out in the bucket is equivalent to how much? 200 minus 100 is equivalent to 100 megabits. So at every second, you are going to have 100 megabits left out in the bucket. So in order to make sure you're able to capture these 100 megabits also, the size of the buffer should be 100 megabits. Therefore, 5 is also equivalent to 100 megabits. Okay, so the answer here for this is D. All right. Now for the last question. I mean, if you have any questions in the previous one, you can let me know. Not, let's move on. See, this what I've explained here is a easier way of getting this question done. So you have multiple such, you can multiple such questions could be asked, but to think about it logically like this, you can answer it easily. Okay, so now question number 5 is consider 4 users U1, U2, U3, U4. U1, U2, U3, U4. And by the way, this is about resource sharing. I'm running out of time, so I'm going fast. Sharing. Okay. U1 needs how many? What is the bandwidth demand of U1? It is 2 Mbps, and U2 is having 2.6 Mbps, and U3 is having 4 Mbps, and U4 is having 5 Mbps. Not having, needs. Their need is this much. Okay, how much do we have? Do we have? We have 10 Mbps. This is 10. The router to which these users connect has a total bandwidth of 10 Mbps. This 10 Mbps has to be shared among these 4 people. Right? What proportion of bandwidth is allocated to user U4? How much is given to U4 when the router uses the min-max pair scheduling algorithm? If you want to look at what min-max pair scheduling algorithm is, you can go and take a look at the traffic management video that there in the NPTEL lectures. It's explained there. Now let's go at it the logical viewpoint. We have 10 Mbps, right? Now there are 4 people, so logically I can divide 10 by 4, which is equivalent to 2.5 Mbps per person. Okay, now what will happen if I give 2.5, 2.5, 2.5, 2.5? Let's see. If I'm giving 2.5 for him, 2.5 for him, 2.5 for him, 2.5 for him, then what happens is you are wasting some resources here. How much you're wasting? You're wasting 0.5 Mbps over there, right? So this is not the best way to allocate. Now, let us minimize certain things and let us maximize certain things. So in this case, you have, sorry, you need to minimize here, right? You need to maximize it. You need to maximize it. You need to maximize it. So we're minimizing wherever it is not required, and we're maximizing as much as possible wherever it is required. Correct. So how do we go ahead doing that? We go by the 3 tenets of min-max sharing, 3 rules. For the first rule, the resources are allocated in the order of increasing demand. Okay. Second rule is no source gets the resource share larger than its demand. The third rule is sources satisfied demand get an equal share of the resource. Okay. Right. Okay. Now you'll understand what this means. So resources are allocated in the order of increasing demand. So in terms of demand, this is the order of increasing demand. Okay. Now we have to first allocate to U1, U2, U3, and then U4. So no resource gets a share larger than its demand. Share larger than its demand. Which means U1 has 2 means it will get at the max of 2, not more than that. And resources with unsatisfied demand get an equal share of the resource. If by any chance we are not able to allocate enough to a particular resource, then we have to divide the resource equally and give it to those users. Now we'll understand what that means. Okay. So let's write this again. 1, 2, 2, 6, 3, 4, 4 is 5 Mbps. Okay, 2.6 and 5. How much do we have? We have 10. Okay. As usual, step 1, divide the total by number of users or number of people that have been divided upon. So how much is that? 10 by 4 is equal to 2.5. Now the problem is if we give 2.5 directly, then it's a waste. So what I'll do, I'm taking 2.5, okay, and I will only be giving 2 of this. So minus 2 is equivalent to 0.5. So I have allocated 2 Mbps. So once I've allocated 2, how much is left out? What is left out is left out is 10 minus 2 is equivalent to 8. This 10 is total, right? Total, I've only allocated 2. So 8 is left out. Now for step 2, I have 8 Mbps in my hands. Now, what do I do with 8? We again, so now one user is done. Now how many are remaining? 3. So I divide 8 by 3. It gives 2.666, whatever. It just keep that. So with among these 3 users, 2.666 is there. So can I allocate 2.6 to any of these? Yes, I can allocate. So I'm allocating 2.6 Mbps to these 2 people. Right. Now, how much is that? How much have I allocated? I have basically allocated 2 plus 2.6 Mbps has been allocated. Just 4.6 Mbps has been allocated. Right. So because I have allocated 2.6, so here what is left out? It is left out from the share is equal to 2.666 minus 2.6 is equal to 0.066. So this much is left out. Right. So for step 3, we have how much? We have 10 minus, okay, We have 6 has been allocated. We have 8, and how much did we allocate? We allocated, yeah, we have total of 8, right? And then we allocated how much to this thing? We allocated 2.6. 2.6 we allocated, and then just give me a moment. 2.6. If somebody knows where I'm going wrong, let me know.
So now 4.6 has been allocated. So 10 minus 4.6, which will be 5.4.
Right, exactly. It's supposed to be 5.4, but that is not the case. Just logically, we're going right now, right? So it's supposed to be the case. Zero six six. Okay, 0.066 is. So basically, I have the solutions here. I've not worked out before. So they're saying is 8 minus 2.666 plus 0.066. This is going to be the budget that's left out. 334. I'm wondering how this number came up. .5 was allocated. Okay, I think solutions are wrong. I'm not wrong. Okay, let's go in our direction and then let us see what the answer is. So as Vineet was saying, so 8 minus how much was allocated? So what was allocated was 2.6.
4.6.
What is how much? 4 point. How much is it? 4 point?
No, so 8. Yeah, it was 5.4, I guess. Yeah.
4, right. Is equivalent to 5.4. So that's the budget that we have in our hands. Let's go in this direction. Let us see what the answer. So for step 3, we have 5.4 in our hands. So 5.4. Now how many people are left out? 2 people are left out. 5.4 divided by 2 is how much?
2.7.
2.7. 7. This is what we have right now. And because both of these need more than 2.7, right? So they need 4 and they need 5. So what does the third rule say? Sources with unsatisfied demands, which means those demands are more than what we have in our hands, they get an equal share. So we just like that we allocate 2.7 Mbps. Now if we sum all of these up, it should sum up to 10 Mbps. Is it happening? Check. If it is not, we will mistake. It makes sense, right? You're allocating something. That means it needs to.
Yes, it is coming as 10.
Right. So it's coming to 10. Right. So this should be the allocation as per me. So in the answers, you have the answer is C for the documentation. It is very close to 7. Sorry, this is okay. Fine, fine. So, what are they asking? They're asking how much does U4 get? U4 is getting how much? 2.7. So the answer is 2.7, and this is supposed to be 2.7. But let me also write out the official answer so that you can compare, right? So the official answer is this. I'll try and find out the correct answer first. So I'll just write this and then we'll push off. Okay, so it'll be late. Okay. So capacity. They say capacity by number, which is equal to 10 by 4, which is equal to 2.5. So far, so good. Every unit is Mbps. Okay, so I'm not going to write Mbps. So because U1 is demand is large, so what they're saying is I'll be allocating only 2 from this. So what is left out? Left out is 0.5. So the formula is like this: 10 is C minus 2.5 plus 0.5. So why 0.5? So I've allocated 2.5 and I'm also getting back 0.5 from it, correct? So it's pretty much the same thing that we did. Now this comes to 8. Step 1 is fine, it's good. Now next is step 1. Step 2 is we have 8 in hand. So how many people are there? 3 are there. 8 divided by 3 is 2.666. So this has to be given among 3 people, right? Among 3 people. And because user 2 needs something less than 2.666, then I need to give only what he requires. How much does user 2 require? He needs only 2.6. User 2 requires 2 requires 2.6. It requires only 2.6. So what they're saying, I've allocated 2.6. So how much is the excess? The excess is 2.666, which is what we have in our hands. Sorry, which is what we have decided for a particular share, minus 2.6. How much does it come to? To 0.066. Yeah. Now we have this value and we have the total, which is 8. So following the same formula, 8 minus 2.666 plus 0.066, right? What is the excess? How much have you actually tried to give them? So this is where I think there is an error either in the solution or in my understanding. But anyway, I'll just write down the answer so that you can choose which one you want to go with. So this comes to how much? 5.334. Okay. Now this is what we have in our hands. For step 3, we have 5.334 that we have to divide among how many? 2 people. Correct. So how much does this come to? This comes to 2.665. So 5.34 divided by 2 is 0.34 divided by 2 is 2.66. 667, but this is 665. Okay, I'm just writing down the official solution. Okay. 2.65, and because the other two users have greater demands, so just like I'm going to allocate 2.665, and that is the answer, 2.665. Now I'll be sharing this PDF also, so if at all you have doubts, you can go through the video and you can see which one is correct. I'll try to confirm this by the next week and give you the correct answer. Right? All right. So I think that's the end of it. We've looked at all the previous questions, and yes, you're done. You're done. Okay then. See, if you have any questions, you can ask me now, or we can push off. It's a little late. Thank you. Bye.
Thank you. Yeah, Harish.
Yeah.
Yeah, I just want to know whether the examination questions will be similar like what we are discussing here.
Um. So I'm for the first time. I've
Huh.
so the exact actually don't have a clue, but I think we can expect it to be similar to the assignment question. By the way, it is descriptive, right? Your examination,
Yeah, I guess. Yeah, I guess
or maybe it's not. I don't. I think I'll get some more information on this. I have no clue. How kind of question.
Yeah, if
Uh,
that just if you can just share that detail as well, then that would.
sure. So the point is, you have certain assignment questions. So the higher probability here is to always look at the assignment question, model your preparation based on the assignment question. So
Oh,
that is the best way to move forward. First, cover the base, which is going to be assignment question, and then move ahead from there. And by ahead, you can probably look at some gate questions. I think this is one. This is a gate. This is a gate question. Be sure with these questions, and then you move on.
sure. Okay. Thank you.
Okay.